You ever watch one of those incredibly complex robots and just wonder how it all works? I mean, how does it move with that kind of precision? How does it seem to just know what to do? It honestly feels like magic. But behind every single thinking, moving machine, there's a secret blueprint. And today, we're going to unpack exactly what that is.
It all boils down to this one question, right? How do engineers get from a pile of circuits, gears, and metal parts to a machine that can assemble a car, explore another planet, or even perform surgery? Well, the secret is the most important work happens long before anyone even picks up a screwdriver.
And that secret process is called modeling and analysis. The best way to think about it is like a language. It's the language engineers use to talk to a robot before it even exists. It's a digital blueprint that lets them predict, test, and perfect every little thing about the robot's behavior, all inside a computer. And this blueprint, it stands on four key pillars.
Okay, our first pillar is kinematics. It's a fancy word, but it's all about the geometry of motion. See, before we can figure out how a robot moves with force and power, we have to answer a much simpler question first. Just where can it move? So kinematics is basically the robot's rulebook for movement. It maps out how all the joints and links connect to figure out its reach, its range of motion, the whole shebang. It's pure geometry. We're not thinking about things like gravity or friction or how heavy an object is. Not yet. We're just creating the map.
And you see this map in action all over the place. A factory arm placing a car door with millimeter precision? Yep, that's kinematics. A surgical robot making a super delicate incision? That's kinematics too. A humanoid robot that can actually walk without falling on its face? You guessed it. That's kinematics making sure it all stays balanced and coordinated.
And that's really the bottom line here. Kinematics is the absolute foundation for any task that demands accuracy. It's what gives a robot its fundamental ability to interact precisely with the world around it, whether it's grabbing a tiny screw or assembling a huge jet engine. Okay, so we've got the map of every possible move the robot can make. But now we've got to bring it into the real world, with physics, force, and all the stuff that's going to push and pull on our robot. Welcome to the world of dynamics. Right. So if kinematics is the map, you can think of dynamics as the physics engine. It answers all of the tough questions, like what happens when a huge gust of wind hits our drone? How much power do the motors actually need to lift this heavy box? How's the robot going to behave when it suddenly speeds up or slams on the brakes? And this is where the rubber really meets the road. A drone uses its dynamic model to fight against the wind and stay perfectly still for that camera shot. An industrial robot has to account for the heavy weight of a welding tool to make sure it doesn't mess up its path. And an autonomous car? It uses dynamics to figure out exactly how long it'll take to stop on a wet road versus a dry one. And this all gets to the most important job of dynamics, making sure the robot is safe and stable. You see, a robot that only knows kinematics might try to lift something way too heavy and literally break itself. But a robot that understands dynamics knows its limits. It knows what it can handle, which means it can do its job safely and reliably. All right, so our robot knows where it can move and it knows how forces are going to affect it. But how does it actually decide what to do from one moment to the next? Well, that brings us to our third and maybe the most fascinating pillar, the robot's brain, or what we call its control system. This is where it starts to feel like real intelligence. Control systems are the algorithms, the software, that take in all the data from the robot sensors, its cameras, its microphones, its touch sensors, and then make decisions in real time. This is what makes a robot more than just a simple machine repeating a task. It makes it adaptive. Just think about a Mars rover. It can't exactly phone home for instructions every time it sees a new rock. Its control system has to make the call, right then and there, to go around it. Or in a crazy, busy warehouse, robots are constantly talking to each other, their control systems making sure they don't crash. And social robots, they can actually listen to you speak and change what they're doing. That is adaptive control, right there. So the huge idea here is adaptation. Great control systems turn robots from pre-programmed puppets into beings that can actually handle uncertainty. They can react to a messy, changing world, which is absolutely critical for any robot that has to work outside of a perfectly predictable factory. Okay, we have the geometry, we have the physics, and we have the brain. But there's one last, really fundamental piece of this puzzle. Can the robot's physical body, its actual metal and plastic parts, handle the job we're going to give it? This is where structural modeling comes in. This is basically the engineering gut check. It's about analyzing the materials, the shape of every component,
and all the physical stress and strain that robot is going to face day in and day out. It's about building a machine that doesn't just work on day one, but is still working perfectly on day 1000.
And the demands here can be absolutely mind-blowing. An exoskeleton has to be strong enough to support a person's entire body weight, but also light enough to actually be worn. An underwater robot has to be built to withstand pressure that would crush a car like a soda can. Even something like an agricultural robot needs careful design so it can grip a tomato firmly enough to pick it, but gently enough not to turn it into ketchup.
So, at the end of the day, this part is all about trust. Structural modeling is what ensures that the super smart robot we've designed is also tough and robust. It guarantees our machine isn't just a clever prototype, but a reliable tool you can count on.
So there we go. 4 very different pillars, right? But they don't work in isolation, not at all. They all have to come together to form one single, unified blueprint for the robot.
And this table just lays it all out nice and simple. Kinematics asks, where can it move? Dynamics adds the next layer. How does it move with forces? The control system is the brain, asking, how does it adapt? And finally, the all-important structural analysis asks, can it survive the job? Each one builds right on top of the last.
And that, right there, is the real power of this whole process. This 4-part blueprint is what turns an idea, maybe just a sketch on a napkin, into a real, working machine. It's the bridge between human imagination and physical reality, giving robots the precision, adaptability, and resilience they need to actually do their jobs in the real world.
These 4 pillars are the bedrock of robotics as we know it. They've built all the amazing machines we see around us today, but it really makes you think. As robots become even more a part of our daily lives, dealing with all the unpredictability of human environments, what's the next pillar going to be? What new principles will build the robots of tomorrow?